Hello, students. I am Mansi Agarwal, Assistant Professor, ABES Engineering College, Ghaziabad. Today, we will be discussing our next topic of data structure, that is heap sort algorithm. The content of the video will include what is a binary heap, min-max heap, relationship between array indices and tree nodes, heap sort, build max heap, and heapify algorithms. And then we are going to implement this algorithm with the help of C language. And we are also going to analyze the complexity of this algorithm. So binary heap is a heap data structure that takes the form of a binary tree, and it was introduced by J.W.J. Williams in 1964. A binary heap is defined as a binary tree with two additional constraints. And these constraints are shape property and the heap property. A binary heap is a complete binary tree. That is, all the levels of the tree except possibly the last one, the deepest one, are fully filled. And if the last level of the tree is not complete, then the nodes of the tree will be filled from left to right. And according to the heap property, the key stored in each node is either greater than or equal to or less than or equal to the keys in the child nodes. Depending upon the heap property, the binary heaps have been divided into two parts. One is called max heap and another one is called min heap. Max heap is a heap in which each node is greater than its children. Like in this tree, 51 is greater than 48 and 23. And similarly, 48 is greater than 21 and 31. On the other hand, min heap is a binary heap in which each node is less than its children. Like here, 16 is less than 32 and 24. Now, relationship between array indices and tree elements. Now, if we talk about the relationship between array indices and tree elements, suppose there is an array having 6 elements and we want to represent this in the form of a tree. So if we talk about algorithmic representation in which the array indices are starting with 1, if we say that I is a parent node, index I is representing a parent node, then its left child will be represented by 2 into I, and the right child will be represented by 2 into I plus 1. So here we can see that suppose the first element is 10, which is stored at the first index of the array, then its left child will be 2 into 1, that is index 20, that is index 2, and the value stored at index 2 is 20. And similarly, the right child of I will be 2 into I plus 1, that is 2 into 1 plus 1, which gives us the value 3. So the right child of 10 will be the value stored at index 3, that is 25. So the index of 10 is 1, and the index of 20 is 2, and the index of 25 is 3. Similarly, the left child of the node 20 having an index 2 will be 2 into I, that is 4. So the number stored at index 4 will become the left child of this node, and the number stored at index 2 into I plus 1, that is 2 into plus 1, which is 5, will become the right child of this node. So in this way, the element stored in the array can be represented as tree. But when we are going to implement this algorithm and the indexes will start from 0 At that point of time, for any node I, the left child will be represented by 2 into I plus 1. Right child will be represented by 2 into I plus 2. Now, coming on to the heap sort algorithm, the various steps of heap sort includes building a max heap out of a binary tree. Then we have to swap the root node with the last node. Then we have to reduce the heap size by 1 and reheapify the root node. And recursively, the step number 2, 3, and 4 will be executed till the heap size is reduced to 1. Now, in order to have a better understanding of how the heap sort algorithm works, let us take an example. So let us have the array with unsorted elements like 10, 20, 25, 6, 12, and 36. So the first task for us is to construct a binary tree with the help of these elements. So as we know that the first element will become the root node, the first element which is stored at index 1 will become the root node, and the left child will be 2 into I, that is the element stored at index 2, and the right child will be the element stored at index 2 into I plus 1, that is 3. And again for the root node I, if the root node becomes 2, so for this, the left child will be 2 into I, that is the element which is stored at index 4, and the right child will be 2 into I plus 1, that is the element stored at index 5. And then for node 3, the left child will be the element stored at index 6, and further we do not have any element. So this is how the binary tree will be created with the help of array indices. Now, in order to sort these elements with the help of heap sort algorithm, the first step that we have to do is we have to make a max heap. We have to build a max heap out of this tree, out of this heap. We have to make a max heap out of this tree. In order to do this, we will start by comparing the node which is stored at index length a by 2. So here as the length, as we can see that length of a is 6. So length a by 2 will become 3. So for node 3, we have to compare it with its both children. And if this node is lesser than the child node, then we have to swap it with the child node having maximum or the largest value. So here we can see that this 25 is having only one child and the value of this child is larger than the node. So these two values will be swapped. So in the first step, in order to build a max heap, this tree will look like this. Now again, we have to check for the node stored at index 2, that is 20, and we have to heapify it. So I am using a term here, heapify. Heapify means we have to move the node to its correct position such that the subtree formed by this node is a max heap itself, right? Is a max heap itself. So what we have to do is here we have to check 20. We have to compare 20 with its left child and the right child. If any of the node, left child or right child, would have been larger, then this 20 would have been swapped with the larger value. But in this case, none of the child nodes are greater or larger than this 20. So there will be no swap. Now we have to move towards the node which is stored at index 1. So you can see here that we have repeatedly heapified the node number 3, 2, and then 1. So that means we are heapifying from length a by 2 to 1. Okay, length a by 2 to 1. We are heapifying each node. Now, in order to heapify 10, what we are going to do? We are going to check this 10 again with the left child. The left child is larger. And then we are going to check this value with the right child. Right child is even more larger. So this 10 will be replaced by 36. This 10 will be replaced by, swapped by 36. So the situation will be, this will become 36. This will become 10. But again, because the swapping has happened, we have to again check this number and we have to again heapify this node. In order to heapify this node again, we will check it with its left child and the right child. And again, as you can see that left child is greater. So it will be swapped with the left child. And there is no right child. There is no right child. So we do not have to compare it with the right child of the node. So this is how we have created a max heap of this tree, right? This is how we had made a max heap of this tree in which we started heapifying the node from length a by 2 down to 1. And in order to heapify what we are doing, we are comparing the node with the left child and the right child. And we are swapping the node with either left child or right child, whichever is having the maximum value. And if the node itself is larger, then there will be no swap. Right? So this is the first step in which we have created the build max heap. Now, after this step, what we are going to do is, as you know that this is the tree which is formed after converting it into a max heap, we are going to swap the root node with the last node. Okay? We are going to swap the root node with the last node such that this will become 10, this will become 36, right? So the array will look like this. 36 will be swapped by 10 and the state of the array will be like this: 10, 20, 25, 6, 12 and 36. Now at this point of time, we have to reduce the size of the array by 1. As you can see that 36 has reached to its right position. So the node 36 will be considered as already sorted and the size of the heap will be reduced by 1. Now again, the situation of the tree is 10, 20, 6, 12 and 25. Now again what we have to do is we have to heapify it only at the root node. We are going to heapify it only at the root node, right? We have to heapify this tree only at the root node. Now after heapification, what will happen? After heapification, this 10 will be compared with the left child and the right child. And so this 10 will be swapped with 25. So this will become 25 and this will become 10. So this will become 25 and this will become 10, right? And again, we have to swap the root node with the last node. That means this will become 12. This will become 25. So this will become 12. The first element will become 12 and the last element will become 25. And you can see that now 25 has also reached to its appropriate position. And then we have to reduce the size of the heap. Right? Now this is the situation. Again, we have already fixed 36 and 25, right? We have already fixed them. And now again, we have to heapify at 12. Now, in order to heapify at 12, 12 will be compared with both the children. Now comparing it with 20 and 10, 20 is larger than 12, so it will be swapped. This will become 20, and here it will become 12. Repeatedly, 12 will be compared with its left child and right child, but here the left child is smaller than 12 and the right child does not exist. So there will be no difference. The only difference is 12 and 20 have been swapped. So this will become 20 and this will become 12. So this is how we have again created the max heap. Now the root node will be swapped with the last node. So this will become 20 and this will become 6, right? So this will become, here it will become 6, here will be 20. And then we have to again reduce the size such that 20, 25 and 36 are already sorted. So this node will also be deleted, having a value 20. Right? Now, this is the situation. Already 20, 25 and 36 are fixed. Again, we have to heapify at the root node. Here, the 6 will be compared with the left child and the right child. And as 12 is the largest value, the 6 will be swapped with 12. So this will become 12 and this will become 6. Right? This will become 12 and this will become 6. And again, this 12 root node will be swapped with the last value. So the last value is 10. Last node of the tree is 10. So this 12 will be swapped with 10. So now the array will look like this will become 10. This will become 12. And at this point of time, again, we will delete this node. We will reduce. We will not delete, but we will reduce the size of the array such that 12, 20, 25 and 36 are now sorted. And the array will have only 2 nodes, that is 10 and 6. Now, again, we have to heapify the root node. In order to heapify the root node, 10 will be compared with the left child. There is no right child. And the left child is smaller. So there will be no swapping. There will be no swapping in heapification. But then after heapification, we have to swap the root node with the last node. So the root node is 10 and we have to swap it with the last node, which is 6. So this will be the situation. This will become 6 and this will become 10. And then we will reduce the size of the heap by 1. And so 10, 12, 20, 25 and 36 are sorted. At this point of time, we are left with only one node and there is no need of further heapification as this node is already sorted. Now, let us now try to make the algorithm of this heap sort technique, right? So in order to make the algorithm, let us first see how any node is heapified, right? How any node is heapified. Let us first make the heapifying algorithm. So if I say that the name of the algorithm is max heapify, suppose I say that the name of the algorithm is max heapify, what all parameters are required for this heapification? Definitely we need the array in which we have to find out the node and we have to heapify it. And then we should know the index of the node that we want to heapify, right? Now what we were supposed to do? We were supposed to check the ith node, the value stored at the ith node with the left child and the right child. So first we will compute the left child, which is going to be 2 into I. And then we are going to compute the right child, which is going to be 2 into I plus 1. And we are storing the node I index in largest, such that we can compare largest with the left and the right. Now for comparison, I already told you that we have to check whether the left child even exists or not. We have to compare the largest with the left child, the node with the left child first. And for that, we have to first check whether the left child even exists or not. For this, how will we check whether the left child exists or not? If the value of left is less than or equal to, if it is less than or equal to length of A, then that means there exists a left child, right? And the second thing that we have to check is whether the value of A left, array left, the value stored at left index, if it is greater than the value which is stored at the largest index, then we can say that the left child is greater than the node itself. And in this case, we can say that largest can have the value of left index, right? In the similar way, we can compare the right child. First of all, we will check whether there exists a right child or not. For this, we can say that if right is less than length of A, then we can say that the right child, yes, the right child exists. And if it exists, then we have to check whether the value which is stored at the index right is greater than A largest or not. If it is greater than A largest, then we can now say that right child is the largest among node left and right. And in this case, largest should have the index of right child. Isn't it? Now, if anyways we have got another largest other than I, we have got value at any other index which is largest than the value stored at I, then in that case, we are going to swap I with the largest, right? So how will we check this? How will we check this? We will check whether we have got any new largest or not. So if the value of largest is no longer equal to I, then we can say that we have found another largest, whether it can be a left child or the right child, right? So in this case, we can say that we have to swap AI, we have to swap AI and A largest. But we saw in the earlier example that even after swapping, if there are still left child and right child of the largest, then we have to again heapify it, and we have to again check it with its left child and the right child. So how this can be done? This is a very important step. How this can be done? This can be done by again calling this heapify function. The name of the function is max heapify. This can be done by again calling this max heapify function with the same array, but we are now heapifying the swapped value, right? And the swapped value is nothing but the value which is stored at index largest. So we have to again heapify the array with the node index largest. So this is the only procedure of heapifying any node, right? This is the procedure of heapifying any node. Now, as you know that in order to perform heap sort, if we say that this is the algorithm to perform heap sort on any array A, what did we saw? We saw that first of all, we have to build a max heap out of it, right? So if I say that heap sort algorithm has started for array A, the first step will be we have to call a function in order to make a max heap. So I can say that we are calling a function build max heap, right? Build max heap for A, isn't it? Build max heap for A. Now what this build max heap is going to do? What this build max heap is going to do? What this build max heap is going to do is this build max heap, you can just write it over here. This build max heap on array A is going to heapify the nodes from length A by 2 down to 1. Isn't it what we have to do while making a max heap? We have to heapify the nodes from length A by 2, from length A by 2 down to 1. And we have to only call this max heapify function. We have to only call this max heapify function for this array and for ith node, right? As we saw in the example, that we have to start by heapifying the node number 3, which was present at length A by 2, right? So in the build max heap algorithm, we are only going to repeatedly, iteratively heapify the nodes from length A by 2 down to 1. Now, after making a max heap, after creation of a max heap, what we have to do? We have to repeatedly swap the root node with the last node, and then we have to heapify the root node. So for this, we can say that for I taking up the value from length A down to 2, because the last node need not to be swapped, down to 2, we have to swap A of I, that is the last node, with A of 1, which is going to be the root node, right? And afterwards, we have to reduce the size. So we can say that if the size is given by A dot heap size, then we have to reduce it. And after this, we have to again heapify. That is, we have to again call the max heapify function with A and root node. So root node will always be 1. So these are 3 algorithms that will work for heap sort, that is heap sort, build max heap, and max heapify. So this is the heap sort algorithm, which I have already discussed with you. This is build max heap, in which we have to repeatedly call the max heapify function from length A by 2 down to 1. And this is max heapify, in which we are taking largest at I, and then we are calculating left and right, and we are comparing it with the child node. And then we are swapping. If we are getting any larger value in the children, we are swapping it. And repeatedly, we are calling the max heapify function. Let us now see the complexity of heap sort algorithm. Suppose this is a perfect binary tree. So for a perfect binary tree, if we see the number of nodes at any level or at any height, if the height of the tree is, suppose if it is 3. So at height 3, we can say that the number of nodes are 1. At height 2, we can say that the number of nodes becomes 2. At height 1, the number of nodes become 4. And at height 0, the number of nodes becomes 8. So here we can say that for a perfect binary tree, we can say that at any level h, the maximum number of nodes can be given by n upon 2 raised to the power h plus 1. And the ceiling of this value, we can say that the number of nodes, if it is represented by n, then the number of nodes at any height h will be given by ceiling of n upon 2 raised to the power h plus 1. Like in this case, we can see that if here the number of nodes are 15, right? Now, if I want to compute the number of nodes that are stored at height 0, then it will be 15 upon 2 raised to the power 0 plus 1, which will give you 7.5. And the ceiling of 7.5 is nothing but 8. Right? Now we can say that for an almost complete binary tree, the number of nodes at any level will always be less than ceiling of n upon 2 raised to the power h plus 1, right? Because in case of the almost complete binary tree, there may be a case that the last level is not complete. So in this case, the maximum number of nodes will always be less than ceiling n upon 2 raised to the power h plus 1. Now, if we talk about the time complexity of max heapify function, so if I consider the worst case, there may be a case in which the node has to be swapped with every node with every node in the height of the tree. This is the worst case, right? So in the worst case of heapification, if we want to heapify this node, this may have to be swapped with this node and then with this node, right? So here we can say that the time complexity of max heapifying a node at height h will be given by OH. This is in the worst case, where h is represented by log n in case of a complete binary tree, right? H is represented by log n in case of a complete binary tree. Now, if we talk about the build max heap algorithm, the total time or the total work done at any level h will be represented by the number of nodes in that level, that is equals to ceiling of n upon 2 raised to the power h plus 1 into the time complexity required to heapify each node, right? So this is given by O of h. So the total time or the total work done at any level, at any height h will be given by ceiling n upon 2 raised to the power h plus 1 into O of h. So for all levels, I can say that this value becomes summation of h is equals to 0 to log n upon 2 raised to the power h plus 1 dot oh. So we can say that the total time required by build max heap algorithm is summation of h is equals to 0 to log n n upon 2 raised to the power h plus 1 dot oh. And OH can be represented as C of h, that is constant of h. We know this by the definition of asymptotic notations. Now, this can be written as we can see here that C and N are constant. We can take them out. And 2 is also constant. This is equals to summation of H is equals to 0 to log N. H upon 2 raised to the power H. Now, we can say that this value is going to be always less than O of Cn by 2 summation of H is equals to 0 to infinity H upon 2 raised to the power H. This is going to be always less than this value. Why? Because now the number of levels, the height of the tree, we are tending it to be infinity, till infinity. So definitely this value will be bigger. And here, summation of H is equals to 0 to infinity H upon 2 raised to the power H is represented by 2. It is represented by 2. So this becomes big O of C n by 2 dot 2. Cancelling these two, we can say that, as we can ignore the constant value, we can say that the complexity of build max heap algorithm is nothing but O(n). So if we see that the total time complexity of heap sort, it comes out to be n log n, as the complexity of build max heap algorithm is n, and that of the heapify algorithm, in the worst case, it is log n. So the total time complexity of heap sort algorithm is nothing but n log n. Now let us try to see the code of this algorithm in C language. So here you can see that the program is implemented with the help of a swap function, in which we are using call by reference technique. We have taken 2 pointers A and B, as we want to actually swap the values of the array, right? If we are swapping root with the last element, then they should actually be swapped. And so the value after swapping must be reflected. So that is why we have taken call by reference here. Then implementing the heapify algorithm, we will take 3 parameters, array, n, and I, where array is having the elements which need to be sorted. N is the size of the array, and I is the node, the index that we need to heapify. The largest will have the value I, left will have 2i plus 1. I have already discussed this. And right will have the value 2 into I plus 2. Now we will check whether the left child exists or not. So if left is less than n, and if ARR left is greater than ARR largest, then we are going to assign largest as the index of the left child. So largest will be equal to left. And if right is less than n, and if if the value stored at the right index is greater than the largest value stored at the largest index, then in that case, largest will have the index of right child. So largest is equals to right. If we have found any of the largests, that means if largest is no longer equal to I, then in that case, we will swap AI with A largest. So we will send the address of AI and the address of A largest to the swap function. And again, we have to heapify the largest node, that is the node stored at the largest index. So again, we will recursively call the heapify function with ARR, n, and the largest index. Now, the second function that we made during the algorithm was build max heap. And build max heap is doing nothing other than calling the heapify function from the n by 2 node till the first node. So here, as we are working on the indexes, I will start with n by 2 minus 1, and it will go till 0. And for every I, we will call the heapify function, right? And in the heap sort algorithm, in the heap sort function, we will call the build max heap with the array and the number of elements. And then from the last element till the first element, we are going to, we are going to swap the first element with the last element, and then we are going to call the heapify function. We are going to call the name of the function is heapify here. We are going to call the heapify function from the root node. So therefore, heapify ARR, I, and 0. Afterwards, we can make a function to print the array, sorted array. So here we have taken another user-defined function, print array, and we are using a loop to display the values of the sorted array. Inside the void main, we have taken an array and we have stored the similar value that we were taking. Then we have calculated the number of elements, and then we have called the heap sort with the array and n. And afterwards, we are calling the print array function in order to display the values. Let us try to run this code. Yes. As we have run this code, we have got the values in the sorted form, we have got 6, 10, 12, 20, 25, and 36 with the help of heap sort algorithm. The references taken for this video includes Tenenbaum, Langsam, Augustine, data structures using C and C++, Horowitz and Sahani, fundamentals of data structures, Shom series, and Tareja's data structure using C. Thank you.